Hello, good morning, good afternoon. Today we're going to be creating a truth table that determines the output voltage Vout in terms of A and B for high and low values. In this situation, we're going to be using binary logic, just to let you know off the bat. And this is just because we're kind of just looking at, is the voltage output on? Is it high? Or is it not on? Zero, low? Kind of just based in like the rationale with FETs using controlling currents, and either letting it pass or blocking it. So it's useful information in that sense. Because we're using binary logic, we have to think of 4 scenarios for V out. When A and B are both 0, when A is 0, B is 1, when A is 1, B is 0, when A is 1, B is 1. And we're going to be looking at the circuit, looking at the N channels, the P channels, whether or not they're in series and parallel, all that jazz to kind of determine what we can expect what the out will be based on what A and B are going into, just for a little more background information on these transistors. We know that we have 4 in this case. Each transistor has a gate, a source, a drain, and then also an N or P channel. The gate in this case controls the flow of a current. The source is the charge carrier, and the drain is where the current is going to flow after being modulated by the gate. So another piece of information that's really important to know is this is an N channel or a P channel. On each of the transistors, you can look at the middle wire, whatever you want to call it, to kind of determine this. It's pretty simple. P channels will have an arrow going away from the gate, N channels will have an arrow going towards the gate. The way I kind of like to remember this is just by considering what an N channel and a P channel are and their differences. N channels are using electrons as primary charge carriers. So it's going to have a negative kind of current, or it's looking at negative flow. It's looking at a current. Whereas P channels are holes primary, where the holes are the primary charge carriers as opposed to electrons. So in this case, you're looking at where the positive, you're looking at the opposite of the current, you're looking more at the voltage, the positive flow. So because of that, the arrows are going to be in different directions, and that kind of is a good way just to kind of gauge and wrap your head around it. I don't know if that's the technical reason why there are arrows, but it helps me. Also, feel free if you have any tips and tricks in the comments to leave them down below, because it's just here to help people learn, and in a way that's pretty standardized. But yeah, anyway, so now that we have our P and N channels marked, we can look if they're pull up or if they're pull down. Pull up kind of refers to if it's connected to VDD at the top, first of all and foremost. But generally speaking, in these earlier problems, you can assume that P channels are generally going to be pull up. Now, the pull down channels are the things that are more so connected to this ground. But in this, like I said, in pretty traditional earlier classes in the circuit problem, you're most likely going to expect the N channels to be connected, or N channels to also be pulled down, like in this scenario. The next thing you want to look at is between the P channels and the N channels, what is the relationship that they have? So for the 2 P channels, we know that they're in series, essentially because a source and a drain are connected. And then we know in the pull down situation that these are in parallel because a drain is connected to a drain and a source is connected to a source. So just kind of wrapping your head around it from a layman's perspective, in a parallel situation, you would expect a voltage to go down both at the same time, or to be split among the 2 different transistors. Where in series, you're actually expecting one to feed into the other, right? The voltage or the current, whatever you want to think about it, they are influencing each other. One is happening after each other, and that's essentially how I like to look at it. And it's pretty helpful, but if that doesn't make sense to you, if you just kind of want to go through the problem, you just literally look at if a source is connected to a drain or if a drain is connected to another drain. And so from this, we can kind of look, and we know that in this case, they're enhancement transistors. We know that because of the little lines next to the gate, there will be different rules for different types of transistors, but in this case, we're looking at enhancement ones. There's going to be 4 scenarios, another 4 scenarios we can consider. When pull up is in series, when pull up is in parallel, when pull down is in series, and when pull down is in parallel. Each of these is going to assume different behaviors. about what the Vout is going to look like. So in our case, we know that, and I think it's pronounced pMOS. Anyways, for pMOS in parallel, which is not our case, but one we definitely need to consider, and I'm just putting it out there in case anyone has variations on this kind of problem or variations on this kind of work. Anyways, for pMOS in parallel, we know that if either A or B are 0, either as an or, we can assume that it's going to be pulled out and that Vout is going to be 1. However, if they are in series, we need both of them to be 0 in order for Vout to be 1. Okay, so both as in an and. If you look at our table A and B, you need 0 and 0 in order for Vout to be 1. Now, I kind of mentioned this earlier, I think, but with FETs, you kind of, before assuming behavior, or if you assume behavior of Vout using the pull up with 1, you kind of don't really, and it's Vout is 1, you don't really need to consider what pull down is and for this specific scenario, because essentially, like, you can't have both of them working at the same time. It's a switch, so if the pull up is giving 1, you don't need to consider the other cases, or you don't really need to consider the behavior any further. Anyways, for the nMOS, what we're looking at then is 2 other rules. So in the parallel situation, if nMOS is in parallel, which ours is, what we need to look at is when either are 1, when either A or B are 1, it's going to pull out. It's going to take away from the drain. Essentially, if either A and B are 1, Vout must be 0 for any of the cases that haven't already been addressed or haven't already been reached by the pull up. And then if they are in series, which is not our case, but just to keep in mind, if for further problems, if it's in series, if both A and B are 1, then you can assume Vout is 0. So that would be kind of an and behavior. Both A and B equal 1. Anyways, using this information, we can kind of fill out our Vout table. As mentioned before, the one that's really going to apply to the pull-up, our pMOS behavior, is looking at A equals 0, B equals 0. We know it must be 1. The rest, we know that because it's in series, or because it's in parallel, if either A or B is 1, we can assume Vout is 0. So our truth table is going to look like 1, 0, 0, 0. And just as like a little side thing, we can also say, oh, interesting, we've seen this before. 1, 0, 0, 0, when 1 is in relation to A equals 0, B equals 0, is actually a NOR gate, like the reverse of an OR gate, which would be 0, 1, 1, 1. You take the opposite, you end up with 1, 0, 0, 0. Anyways, this is my first video, so thank you for putting up with the little rockiness and awkward transitions and everything like that. I'm also a student in electrical engineering, so like I said, if there's anything I explained wrong, anything was confusing, please let me know. Very open to feedback. This isn't here to mislead you. This is here to help people. So thanks for getting it through. I had fun, and until next time.